After going through the detailed simulation process, we will switch our attention on how to construct a model. There are different ways to develop models with different objectives. No single approach can perfectly meet all boundary conditions. In this presentation, we focus on the way to construct a simulator-friendly model for fitting experimental data. We will use the B-Simply model as an example, as it was the first industrial standard model adopted by the industry. By going through the process on how a model is developed, I hope this presentation will give you some idea on the basic concepts of device modeling. To begin with, let us recall that the role of a model in a circuit simulation is to produce the currents and conductance of a device when the terminal voltages are given. To construct a MOSFET model, we can use the classical equations of a MOSFET to begin with. When the MOSFET is turned on, the current of a MOSFET in the linear region is given by the equation here. This equation only applies when the MOSFET is turned on and the gate voltage is larger than Vt. The behavior of this equation at the particular Vg is shown in this figure on the right. When the drain voltage becomes larger than Vg minus Vt, the equation predicts the current to decrease, which is non-physical. So, the saturation region equation given below is introduced to keep the current to be constant for Vd larger than Vg minus Vt. This is called the saturation region current equation, and the voltage Vg minus Vt is called the saturation drain voltage. When Vg is below Vt, we assume that the MOSFET is perfectly turned off and set the current to be zero. After introducing the third equation, the current with respect to Vg at the particular Vd is given on the right. With these three equations, there are two breakpoints that one will switch to the other. They are located at Vg equal to Vt and Vd equal to Vg minus Vt. We have to check the currents and conductance at both breakpoints to make sure they are continuous. Fortunately, they are in this case. So the classical MOSFET equations form a reasonable model for circuit simulation. However, we know that the classical equations are not accurate enough. In particular, the current of a MOSFET below the threshold voltage Vt is non-zero. We can modify the drain current equation for Vg less than Vt to be an exponential equation with respect to Vg, which is physically derived and given here. At the same time, we keep the same equations when the MOSFET is turned on. With the new equations, we can look at the predicted behavior of the MOSFET with respect to Vg using the earlier figure as a reference. For the region with Vg below Vt, the current is no longer zero, and it is given by the red line shown in the figure. There will be a discontinuity in the current at Vg equal to Vt. The discontinuity will become more obvious when plotting the current in log scale, which is given in the graph below. This kind of behavior is not acceptable, and we have to find a way to remove the discontinuity. We know that the actual current will change from the exponential characteristics to the linear characteristics as shown in the blue line in the graph. The question is how to provide such transition. In general, there are two different methods to handle it. The first method is to derive more accurate equations based on the device physics. For example, using the surface potential approach, we can derive the current equations as given here, which is much more complicated than the simple model. This approach has some drawbacks. First of all, the equations used to calculate the surface potential phi s at the source and drain are transcendental equations without explicit form. So, iteration is needed to solve the surface potential, and it is not very simulation friendly. However, the number of iterations can be reduced by providing an appropriate initial guess. Secondly, the complex form of the equation makes it difficult to adjust part of the curve while not affecting the other parts. For example, assume the turn-on region is accurately predicted already, and only the suppressor region need to be adjusted. It is difficult just to change some parameters to adjust the suppressor region without affecting the on region. The second approach is to connect the two equations using a smoothing function in the transition region. The transition need to ensure the current and conductance are smooth and continuous. This is not a simple task, and it may need a lot of parameters to adjust the transition function to meet the criteria at the boundary points. Also, the transition needs to maintain the correct characteristics not only for one drain voltage, but all drain voltages. The BC models use the smoothing function approach, but all the smoothing functions are not satisfactory until the third version of the BC family, the BC3 model. In BC3, a naturally smooth function that transits from exponential to linear dependence on the running variable is used to achieve the smooth transition. It defines a variable called VGST effective given by the expression here, where VTH is the thermal voltage KT over Q, and N is the ideality vector. After VGST effective is defined, it will be used to replace all the Vg minus Vt in the on region equations. The suppressor region equation is no longer necessary, as VGST effective is always positive. As a result, the on region equations can be extended to the case with Vg less than Vt. Let's take a look how the smoothing function works. When Vg minus Vt becomes very large, and much larger than 2nV thermal, the exponential term becomes very large as well. Then, the 1 in the parenthesis can be. After removing the 1, the natural log and the exponential cancel out each other, and the 2nV thermal terms also cancel out each other. In such case, VGST effective becomes very close to Vg minus Vt. The on-region current equations just give the value of the basic MOSFET model, as shown with the blue line in the given figure. When Vg becomes smaller than Vt, Vg minus Vt becomes negative, and it is on the other side of the line Vg equal to Vt. When the magnitude of Vg minus Vt becomes much larger than 2nV thermal, the index of the exponential term becomes a very large negative number, and the exponential term becomes a very small positive number. We can express the quantity inside the logarithmic term to be 1 plus x, where x is a very small number given by the exponential term. We can then expand the natural log of 1 plus x. The following series will be obtained. Assuming x is very small, we can ignore all the second-order terms onward, and we will have natural log 1 plus x approximately just equal to x. Putting it back into the original equation, VGST effective equal to the expression given here, with an exponential dependent on Vg. In the suppressor region, VGST effective will be very small, and it is most probably to have Vd larger than VGST effective. So, we can safely substitute the value of VGST effective to the saturation region equations, and it will become the following. As shown by the equation, the drain current will have an exponential dependent on the gate voltage. It will give an exponential trend in the graph as shown here. The trend is now correct, with the current follows an exponential function at Vg below Vt, and finally becomes linear at high Vg. However, the magnitude of the current in the suppressor region may not be correct. It is because there is no parameter to tune the current in the suppressor region, and the property of the equation is fixed by the values from the on-region equation. Some might propose to change the expression of VGST effective. However, this is also difficult, because any small changes to the expression can cause incomplete cancellation of the constants. That will affect the convergence of VGST effective to Vg minus Vt. This in turn affects the accuracy of the on-region model. To achieve better fitting in the suppressor region, the VGST effective function used in BSIM3 is given here. The purpose of this complicated function is just to introduce a fitting parameter V off to provide an offset to the voltage axis in the suppressor current. The quantity in front of the exponential term in the denominator is to provide some physical meaning to the expression. But it is not important, as it can be absorbed into V off, which is an arbitrary fitting parameter anyway. Now, let's look at the behavior of the new VGST effective. When Vg minus Vt minus 2V off becomes much larger than 2mV thermal, the index of the exponential term in the denominator becomes very negative, and the exponential term will become very small and can be ignored. So, VGST effective just pick up the value of the numerator, which is the same as what is given before. Depending on the value of V off, which assumed to be relatively small, the conditions also imply the exponential term in the expression to be much larger than 1. VGST effective will again be approximated to Vg minus Vt. Therefore, in the region with Vg larger than Vt, the current equation will follow the prediction of the conventional equations as shown in the graph. As the denominator is always larger than 1, you may expect the current calculated with the new VGST effective will always be slightly less than that calculated with the original VGST effective function. When Vg minus Vt minus 2V off becomes very negative compared with minus 2mV thermal, the exponential term in the denominator will become very large, and the 1 in the denominator can be removed. The natural log and exponential function in the numerator can be approximated by an exponential function like what is discussed before. Then, the exponential function in the numerator and denominator can be combined to give the following expression. It shows that the V off term provides an offset to the variable Vg in the suppressor region of the equation, but not affecting the on region. By adjusting the value of V off, the suppressor region curve can be arbitrarily shifted to either directions to match the physical data provided. Another nice property of this approach is the function becomes infinitely differentiable, and we no longer need to worry about the continuity of the function and all its derivatives. After introducing the VGST effective function, the equation to describe the MOSFET behavior reduces from 3 to 2. However, as long as there is a switching between two functions, there is a potential concern at the boundary point. In particular, due to the effect of velocity saturation, the switchover point from the linear region to the saturation region will occur at the saturation drain voltage VD set, which is smaller than the VGST effective. The new characteristics is shown in the figure. While the current is still continuous after adjusting the saturation drain current, but the derivatives at the VD set point becomes discontinuous. To ensure the continuity and smoothness of the function and its derivatives, another smoothing function is used. The smoothing function used is given here, using a new variable VD effective given by the expression here. Then, the VDS effective is used to replace the VD term in the linear region MOSFET equation. After doing it, the saturation region equation is no longer needed, and one equation can be used to calculate the MOSFET current in all operation regions. The characteristic of VDS effective is shown in the figure here. From the figure, it can be seen that at small VDS, smaller than VD set, VDS effective is just approximately equal to. When VDS becomes larger than VD set, VDS effective will be clamped at VD set. The value of delta controls the abruptness of the transition. The property of the function can be easily verified by using any software like Excel or MATLAB, which I will not cover here. With the introduction of both VGST effective and VDS effective, the drain current of a MOSFET can now be described by one single equation to ensure the smoothness of the function and derivatives. After going through the approach to develop a simulator-friendly model, the next issue to be addressed is the way to improve the model accuracy for a wide range of geometries and biases. To understand how this can be achieved, we will use the process to develop the threshold voltage model as an example. I will demonstrate how to enable it to match a wide range of existing data. To begin the process, we first measure the drain current of a typical MOSFET with data to be matched as a function of gate voltage at very small drain voltage, say 50 millivolt. Then, we found the maximum slope of the graph, which corresponds to the maximum transconductance Gm. Extending the slope and let it meet the Vg axis. This gives the measured threshold voltage that we call Vt0. It is the initial Vt we obtained. Vt0 corresponds to the Vt obtained in many textbooks, which is given by the expression here. But as we do not really know the doping concentration and other related parameters, we obtain it by direct measurement instead. Using Vt0 for the value of Vt indicates that the threshold voltage is a constant, independent of geometry and bias. This is definitely not accurate enough, and we need to improve its accuracy. The threshold voltage actually depends on body bias. When different body bias is applied, the drain current shifts accordingly, leading to different Vt. To account for this, we add one correction, delta Vt1, to the Vt expression. Delta Vt1 is given by the common expression here, where gamma is the body factor, and phi b is the difference between the Fermi level and the intrinsic Fermi level of the silicon substrate. In the process, some new parameters are added to give the correct value of Vt. They are listed here. In the B-sim3 model, the body factor gamma is called K1. Phi b is calculated by other parameters, including the substrate doping and channel doping concentration. But to keep things simple, we just count phi b as an independent parameter in this discussion. The Vt expression we have derived so far can only handle the case with uniform body doping. In real devices, the substrate doping can be non-uniform, as shown in the figure. When different body biases are applied, the depletion region edge passes through different regions with different doping concentration. When we measure the Vt as a function of the square root of 2 phi b minus Vbs, different slopes can be observed due to different doping concentrations resulting in different gamma. To account for this effect, another correction, delta Vt2, is added. And delta Vt2 is given by the expression here, where K2 is another fitting parameter that corrects the value of K1 in some part of the curve. To account for this effect, one additional parameter associated with Vt is added. Now, the Vt expression we have does not have a channel length dependence. When the threshold voltage is plotted against the channel length, the characteristics can look like what is given here. When the channel length is reduced, Vt first increases and then decreases. And the amount of increase and decrease depends on the gate oxide thickness. The part that Vt increases with reduction of channel length is called the reverse short channel effect. The generally accepted explanation is given in the figure below. The channel dopant distribution is non-uniform along the channel length and has higher concentration near the source and drain. It may be due to the halo structure or other processing-related effects. The dopant distribution is assumed to be what is given in the graph at the bottom. When calculating Vt, the dopant concentration should be the average one, instead of the uniform substrate doping Na. To find the average doping concentration, we define the effective doping concentration N effective, which is given by the equation here. It is just the weighted sum of the doping concentration along the channel. After some mathematical manipulation, all the newly introduced parameters can be lumped into a single NLX. And NLX is given by the expression here. As we do not really know what LX and NP are, NLX is just another fitting parameter, even though it bears some physical meaning. After defining NLX, we can formulate the VT increment as delta VT3 with the expression given here. And the updated expression for VT becomes what is given here. The parameter associated with VT is increased by 1, as listed here. After handling the VT increase due to reverse short channel effects, we have to handle the VT drop at even smaller channel length. To do that, an incremental VT4 is introduced with the expression given here. I will not explain the derivation of delta VT4 as it is not the focus of this presentation. In these expressions, three new parameters dVT0, dVT1, and LT are introduced. LT can be further expressed by the following expressions with another new parameters dVT2. After all, one more term is added to the VT expression, and the number of parameters associated with VT is increased by 3. At small channel length, the VT is also dependent on the drain voltage due to drain-induced barrier lowering, or DIBL, as shown in the figure. To incorporate the drain voltage dependence, a delta VT5 is introduced, and VT5 is added as another increment to the VT expression, and 3 more parameters are added to the expression of VT. The process continues to add delta VT6 to account for the width dependence of VT, and 3 more parameters are added. So far, the way we add VT dependence on W and L assume that the changes of VT with respect to L and W are uncorrelated. However, it is not true, as the way VT varies with L at wide channel device and narrow channel device can be different. To account for this correlation, a delta VT7 as a function of the product of W and L is introduced with the expression given here. This delta VT7 is added to the VT expression as well. And the number of parameters is also increased by 3. The process can continue to add other effects of other parameters to VT, such as temperature. The accuracy of the model is improved by adding more parameters. In the process, we notice that usually 3 parameters are added to include the dependence of a new variable. It is because most of the physical quantity has a monotonic dependence on another parameter. In that case, a proper function is selected to match the trend of the data, either concave up or concave down. Then, one parameter is needed to set the initial point, one parameter to set the final point, and one parameter to control the rate of change. This is a very quick and brief example on how to construct a simulator-friendly model and how to improve the model accuracy. But it does cover the most general concept and process on how a model is constructed, without going through the detailed physics.